Chapter 18, temperature. We've so far studied only one area of general physics, and that is mechanics. Starting from this chapter, we're going into the second major area of introductory physics, and that is thermal physics. In thermal physics, we deal with the properties of matter that's associated with temperature change. Okay, everybody understands what temperature means, or you think you understand what temperature means. This entire chapter is dedicated to temperature. We have to look at what temperature means and what happens when temperature changes. Turns out this concept is not as simple and straightforward as some of us might think, but we do understand from common sense that when temperature of a matter changes, things will happen to it. For example, if you look at this example of the 3 states of water, everybody knows that when the temperature is low enough, or more precisely below 0 degrees Celsius or 32 degrees Fahrenheit, it becomes solid, which is called ice. Right? And between 0 degrees Celsius and 100 degrees Celsius, it is liquid water. And above 100 degrees Celsius becomes water vapor or steam. It becomes a gas. Right? That's a very common example of what happens to the state of matter when the temperature changes. Thermal physics deals with the properties of a system associated with this temperature change. And that will be the subject of chapter 18, 19, 20, and 21, the next 4 chapters. It's, again, the second major branch of physics called thermal physics. And again, this chapter is dedicated to mechanics, to temperature. So what does temperature really stand for? Everybody thinks that you know about temperature. A lot of people thought, I know what temperature means. It's the degree of hotness or coldness, right? The colder it is, the lower the temperature, and so on. And we all know that in the summertime is hot, that's the temperature is high, and in wintertime the temperature is low, and that's how we feel cold. But the thing is, can you quantify hotness and coldness? Can you give it a number? And does everybody agree on whether something's hot or something's cold? Or we can even ask the question of whether you, the same person, feels the same hotness and coldness at the same moment. You might think that these are silly questions, but they're not. Look at this example. Okay, suppose I imagine I have 2 cups of water. One is ice cold, the one on the left, this one. That's ice cold. Okay, and then we have another one on the right. That one is very hot. Okay, steamy hot. Now, if you dip your hand into this one on the left, okay, you dip your hand into it, you say, gee, that's cold, right? At the same time, you dip your other hand onto the steamy hot one, you say, gee, this is cold, this is hot. Then you conclude, the temperature of the left one is lower than the temperature of the right one because the left one's colder, the right one is hotter. But my question is, suppose you put these 2 hands, one in the cold water, one in hot water for a while, and then you take them out simultaneously, and very quickly, you dip both hands into a 3rd bucket of water, which is lukewarm. Okay, it's not very cold, not very hot. Now, can you tell me how you feel? Okay, this hand, which came from here, now feels warmer, right? It feels warm. But that one, which came from the hot water, now feels cold. You see that? At the same moment, your 2 hands are telling you a different story. The one that came from the ice water tells you, gee, I feel warm, I feel hot. The one that came from steamy hot water now tells you it feels cold. Which one are you supposed to trust? Now, we all know that a 3rd bucket of water, the temperature is the same for both. Both hands should supposedly feel the same warmth, right? But they don't. Your perception of hotness and coldness depends on the experience, and the 2 hands happen to have had different experiences coming out of different buckets. So you see, hotness and coldness cannot be easily quantified, and it's a very is a very objective sensation. It's not something we can rely as a scientific definition for temperature, let alone quantifying it based on that. Okay, so we need a better way to define temperature. And the funny thing is, you will learn at the end of this entire chapter, even though we dedicate the entire chapter to temperature, the precise definition of temperature is still not given at the end of this chapter. You won't find what temperature truly stands for until 2 chapters down the line, believe it or not. It is a concept that's more complicated than we think, but we still can have a pretty good idea what temperature stands for and how to measure it. Okay, so let's move on. How does one really define temperature? Now, one thing we know for sure is that when you have something cold and something hot, and put them together, you allow energy to exchange between them, okay? Then we know common sense tells us that hot substance will give up energy, okay? And the colder substance will receive energy. So there is a net energy flow from the hot subject to the cold subject, okay? And that happens all the time. We know that. That is called flow of heat. And at the end of the day, when everything is done, no heat is flowing anymore from hot to cold substance, then we say we have reached what's called thermal equilibrium, okay? Thermal equilibrium. So thermal equilibrium is a state where there is no more heat flow or energy flow from part of the substance to another when they are connected, allowed to exchange energy. Okay, and so my question is, what happens when thermal equilibrium has been reached? It's like when you have, when you have 2 cups of water and you connect them with a siphon, and then eventually the water levels will be equalized, right? The water will flow from high to low ground, and eventually, when the 2 sides have the same water level, the water is going to start flowing, right? And so in that case, what happens is you have to look at the water level, and when the water level is equalized, there's no more flow of water. Now, in a case of thermal energy flow, when does thermal energy flow? When is thermal equilibrium reached? Is it because I have a substance with more thermal energy than the other, and that guy must have to give up some of its energy until the 2 substances reach the same amount of the total thermal energy? But the obvious answer is no. You look at the case when you pour a cup of hot water into the ocean. Clearly, this hot water will lose energy because the temperature goes down, as we know, and the surrounding seawater will have a slight raise in temperature because it receives energy. But you look at the total amount of energy held by this little cup of water versus the entire ocean. There is no question the ocean has far more energy than this little cup of water, right? And still energy flew from the water in the cup to the ocean, not because the water in the cup has more energy, but because the temperature is higher, right? And clearly, it's understandable that when no more energy is flowing from hot water to cold water, what they reached is not the total amount of energy being the same, but rather temperature being the same. We all have that experience. So common sense tells us that thermal equilibrium is reached when the 2 parts exchanging thermal energy reaches the same temperature. Okay, so can we think of temperature to be a parameter that's directly related to thermal equilibrium? That would be a good idea, right? So how do we know the 2 substances have the same temperature? Just put them together to see how energy flows. If there's no energy flow anymore, when we say thermal equilibrium has been reached, then we say they must have the same temperature. Okay, that's from common sense. Okay, is that something that's scientifically true? Well, our experience tells us it is true. And then we look at a case like this. Okay, we look at a case like this. I have a substance called A, right? Substance called A here on the left. And suppose I measure its temperature with a thermometer. What a thermometer does is that it'll display a number which tells you quantitatively what temperature is. And that's when the thermometer reaches thermal equilibrium with that substance A. Now, don't worry about how that number is displayed and how it's measured. But we know when that number never doesn't change anymore, it is clear that thermal equilibrium has been reached between the thermometer and the substance A. Now let's call the thermometer, we call it C, okay? That means, according to our logic, the temperature of A equals the temperature of C, right? The thermometer reaches the same temperature as substance A, therefore, thermal equilibrium has been reached and the display will not change anymore. Both the thermometer and the substance A has the same temperature of 22.5 degrees, whatever that temperature scale is. Right? So that means TA equals TC. Okay. So let me write that down. Oops. And TA equals TC because no more energy exchange is happening. They have reached thermal equilibrium. Now, suppose we use the same thermometer and connect to a substance called B, okay? Substance B. And we find, once again, that there is no heat exchange. There is no energy exchange between substance B and the same thermometer. What does that tell us? That tells me that TB is also equal to TC, right? Following my logic, right? Now think about it. Mathematically, if TA equals TC and TB equals TC, then it follows that TA must equal to TB, right? You might think this is just too trivial, right? Well, is it really trivial? We're talking about physics. We're talking about a real lab, real experiment. When temperatures of A and B are the same, then from our understanding, there is not going to be any energy flow, even if you put A and B in direct contact, in direct thermal contact, allowing them to exchange energy. And nothing is going to happen because they've already reached the same temperature. Right? That's something we would hope for. Now, but that's an experiment. You never know what's going to happen until you actually do the experiment. What's going to happen if you actually put A and B together? Look, we have never done that. We have put A and C together, reach the same temperature. We have put B and C together, reach the same temperature. We have never put A and C together. If we did, we should expect nothing to happen in terms of energy exchange because they're already at the same temperature. Is this true? Well, we can do an experiment. We put an A and B together in thermal contact. If there's no energy flow, that's cool because they reach the same temperature. So TA equals TB according to our connection between thermal equilibrium and temperature. What happens, God forbid, what happens if there's a weird situation, energy starts to flow from A to B or from B to A? That means TA is not equal to TB because energy is still flowing, right? Thermal equilibrium hasn't been reached, but that would be logically inconsistent with the fact that TA equals TC and TB equals TC, because that mathematically would infer that TA equals TB, and that's not happening because thermal energy is still flowing from one substance to the other, which means TA is not equal to TB by our definition. Right? So if thermal energy still flows between A and B in our experiment, then our definition of temperature associated with thermal equilibrium will not be logically consistent. So what happens in the real world? It turns out what happens in the real world is that if A and C are already in thermal equilibrium and B and C are already in thermal equilibrium, then I don't care how you put A and B together in thermal equilibrium, no heat flows from A and B or from B to A. Okay, no energy will be exchanged between A and B. That is from countless observations and experiments. So our concept of thermal equilibrium in connection with temperature is a valid concept. Okay, this is an experimental observation from countless experiences. It is not something trivial. It's something from experiment. It's actually a law. It's called a zeroth law of thermodynamics. Now, this is funny. Have you ever heard of something, zeroth law of anything? I haven't, besides this, but it is something, it's actually a legitimate question. What happens when you put A and B together? It's not just a mathematical concept. It's from physics experiment. Fortunately, our counter experiments do tell us that once A and C reaches thermal equilibrium, B and C reach thermal equilibrium, A and B will as well. So it is a valid way of connecting temperature with thermal equilibrium. And that is when two substances are allowed to exchange thermal energy. They will do so until they reach thermal equilibrium, upon which they reach the same what? Temperature. So temperature is a parameter that determines whether something is in thermal equilibrium with another. Right? When they have the same temperature, we say thermal equilibrium has been reached. So this is how we define temperature for now. It's not a full definition yet. As you will see, we must dig a lot deeper than that, but at least it gives us a way to measure temperature. We measure temperature through thermal equilibrium, right? A thermometer is a device that we can connect to a substance in thermal energy exchange. And when thermal equilibrium has been reached between the thermometer and that substance, then we can read a temperature from the thermometer. It's going to be the same temperature as the substance whose temperature we wish to measure. Okay, so let's do that. Okay, how do we measure temperature with a thermometer? Well, the thing is, the measurement of temperature is not as simple as we might think. It's not like measuring the length of something. We measure the length, we say, oh, sure, I have a meter stick. I have a meter stick. The meter stick is defined as 1 meter long, or whatever, however we define that 1 meter, but it's a standard length. And I can use that meter stick to measure the length of anything else. For example, if I measure the length of a table, it turns out to be twice as long as the meter stick. Then we say that length of table is what? Is 2 meters, right? In that case, we're using a standard length, which is a meter, to measure the length of anything else. We're using length to measure length, right? No such luck with temperature. You can never measure temperature directly with another temperature. There's no such a thing. How does a thermometer work? A thermometer, again, is placed in thermal contact with a substance whose temperature you wish to measure. And after a while, it does reach the same temperature. Thermal equilibrium has been established. No energy exchange happens anymore. But how does a thermometer give you a temperature reading? It's not reading from its own temperature directly. It displays a temperature based on some change in its physical property. It's an indirect measurement. For example, look at this glass, look at mercury in glass thermometer or liquid in glass thermometer. Okay, there is a liquid column, as you can see here. Okay, there is this liquid column here. This liquid column, the height of the column will change when you dip it into a substance of different temperature. It's common sense, at least for most substances, the colder it gets, the smaller the volume, right? It shrinks and temperature goes down, and expands when the temperature goes up, right? So when you dip this thermometer into a glass of substance, like in this case, this liquid or this water in that glass tube, the height of this liquid column inside the thermometer will change, will rise or fall depending on the temperature of the water being measured. If it's cold, then the column in the glass thermometer will shrink, so it goes down. If it's hot, then it's going to expand and it goes up, right? So we're using the height of the column to measure the temperature. We're not using temperature itself to measure temperature, okay? It's the physical property associated with temperature that's being exploited to measure temperature. In this case, the thermal expansion of this piece of glass. Okay, look at another example. Digital thermometers. Now that looks even more mysterious because I don't know what, everything is sealed, you cannot tell what's inside. You measure your body temperature, you measure, and so this one is this one is it's in direct thermal contact, right? You can put it inside your mouth, for example. You measure temperature. What is in thermal contact with your mouth? You can measure its temperature. That one is even more mysterious because it can measure temperature over the air, right? It's you put this thing near your forehead, it measures temperature. How do these things work? Again, it's not a direct measurement of temperature. Okay, the one on the left, for example, how does it find this number of 97.5 Fahrenheit? Well, one possibility, one mechanism is that there is an electrical current running inside the thermometer. Okay, and this electrical current, the amount of current that runs through depends on the resistance. Okay, it depends on the resistance of the circuit. And the resistance of a piece of metal is a function of its temperature. The higher the temperature, the more resistive it gets, which means the smaller the current, right? So by measuring the current, if the current falls, that means the resistance is increased, which means the temperature is higher. You see that? So here we're using the thermal, the dependency of the resistance, electrical resistance as a function of temperature instead of thermal expansion of the volume. So again, it's a physical property associated with temperature, not the temperature itself. All right? And the one on the right uses the radiation, electromagnetic radiation associated with temperature. Everything radiates electromagnetic waves at different temperatures. And the higher the temperature, the greater the amount of radiation you get. Okay, so what this thermometer does is that it captures the amount of electromagnetic radiation coming from your forehead, and the greater the amount of radiation it captures, the higher the temperature. Okay, because there's a way to figure out how much temperature is given the intensity of the radiation. Okay, so all these are examples of how thermometers work. They each utilize a certain physical property, which is a function of the temperature. It measures temperature by measuring that physical property, such as the length of the column, such as the resistivity of the metal inside, and so on. Okay, so that's how we measure temperature. It's always an indirect measurement, right? Now, when it comes to temperature, we know there are different temperature scales, just like there are different units for length, like meters, inches, and so on. There are 3 common temperature scales that we should all know about. Okay, Celsius scale is based on water, a common substance, right? So what you do is when you look at a mixture of water and ice, they reach equilibrium, and that only happens at a given temperature point. We call this temperature point 0 degrees Celsius for convenience, okay? And also water becomes steam at another temperature under normal pressure of 1 atm. And that's when water boils at sea level. And then we call that temperature 100 degrees Celsius. Why 0 and 100? It's a matter of convenience, simple numbers, right? So water stays liquid between 0 degrees Celsius and 100 degrees Celsius at 1 atm of air pressure. Okay, so we have 2 fixed points for Celsius scale. These 2 fixed points are the freezing and boiling temperature of water. But for Fahrenheit, these two points have different temperature readings. We call the freezing temperature of water 32 degrees Celsius. I'm sorry, 32 degrees Fahrenheit, not 0 degree Fahrenheit. And the boiling temperature of water on the Fahrenheit scale is not 32, is not 100 degrees. Rather, there's a formula for you to convert between them. You look at that formula here. The Fahrenheit temperature is, you take the Celsius temperature times 9/5 and then plus 32, okay? So if you take T equal to 100 degrees Celsius, that's the boiling temperature of water, times 9, that's 900/5 and plus 32, what you're getting is 212 degrees Fahrenheit. That is the boiling temperature of water on the Fahrenheit scale. Okay, all these have historical reasons, but these are, however you define these are just fixed points on different temperature scales. Okay, Celsius and Fahrenheit, all of these fixed points are arbitrary. They're just based on, historical definitions. There is nothing scientific about it. I don't have to define the 0 degree as the freezing temperature of water or 30 degrees. It doesn't matter, but people already define it, so we can keep it that. But what's scientific is the next one. It's called the Kelvin scale. The Kelvin scale has the same temperature increment unit as Celsius, which means if the temperature increased by 1 degree Celsius, it is the same as 1 Kelvin of temperature increase. By the way, we don't call it Kelvin degrees, we just call it Kelvin. Okay. Kelvin is named after Lord Kelvin, a physicist. He's the only one of these names among Celsius and Fahrenheit and Kelvin. He's the only physicist in the group. And there is a good reason for that. You take Kelvin temperature, which is defined as Celsius temperature plus a specific number, 273.15. That number is scientific. It is not just made up. Okay, why 273.15 precisely? Well, that has to do with what's called an ideal gas. What is an ideal gas? You see that more in the next couple of lectures. But basically, you can think of it as a very dilute gas, okay? When the gas is very dilute, the gas molecules are far apart, relatively speaking, they're far apart, and they do not interact with each other a lot because they don't see each other much, okay? And it turns out when you make a gas very dilute, interesting things will happen when you change its temperature. There are three, for a given amount of gas, there are three parameters that can change. Its pressure, its volume, and its temperature. Okay, now for simplicity, let's fix one of these three parameters. In this case, we're going to fix the volume. Okay, we're going to fix the volume. What happens when the temperature of a certain amount of dilute gas is changed? If you do not allow the volume to change, what's going to happen to its pressure? Well, common sense tells us that if you have the same volume, say a certain amount of gas in a flask, right? You do not change the volume of the flask and you dip it into something very cold, you can imagine that the pressure will go down. But if you heat it up to something very hot, you can expect the pressure to be higher, and it can even actually explode if the temperature is really really high, right? Because the pressure gets really so large that it can cause an explosion. So we can use the pressure reading of a certain amount of dilute gas at a constant volume to measure the temperature, because the pressure and temperature for this dilute gas turns out to be proportional to each other at constant volume. That's called constant volume gas thermometer. Okay, so look at the diagram on the left, right? We have this certain amount of dilute gas. All right, let me highlight what that is. Okay, you have this much gas. You have this much gas all the way here. All right, that's the volume. Now, what happens when you dip this gas, this glass bulb containing the gas into something very cold? Then it wants to shrink. The volume want to get smaller, but we don't allow that to happen. What we do is you look at this this U-tube on the right side of this device. Okay, this U-shaped tube. Okay, this guy right here. It contains some mercury. So what I'm going to do is I'm going to hold this. I'm going to hold this guy here. Okay, I'm going to hold this tube here. I'm going to grab this tube and I'm going to move this tube up and down until at some point, this mercury level stays where it is. Okay, it stays where it is. I mean, it's by adjusting the height of this tube, I can move the tube up and down. I can make sure that this level stays the same. That means the volume of this tank of gas, of this gas trapped in this tube did not change. It's a constant volume. But as a result, the height h in excess of the other side this is how much higher it is, that height h will change. Okay, the greater this h, the greater the pressure of the mercury bearing down, which means the greater the pressure of the gas inside. So you can imagine if I increase the temperature, if I dip this into something hot, okay, then to keep the water level, to keep the mercury level here the same, you're gonna have to increase this height, this column here. And the amount of extra mercury here, H, determines the pressure. We all know what that pressure is. It's rho GH. We learned that back in chapter 14 in the physics of liquids. Rho is the density of mercury. G is the acceleration of gravity. H is this extra column, right? And that tells me how much pressure there is in this gas. And so by measuring H, we can find a pressure inside the gas. And then what happens as you change the temperature? Turns out the pressure will change, and the pressure is proportional to the volume for this dilute gas. I cannot think of this, I cannot easily say that for other substances. For dilute gas, that is true. It's part of what's called ideal gas law that you will learn later. Now, the beauty of this is that it doesn't matter what type of dilute gas you use. You can use helium, mercury, you can use oxygen, you can use nitrogen, you can use any dilute gas, okay? You get the same measurement for temperature. And suppose I take a certain amount of dilute gas, I do a measurement of temperature versus pressure, and I end up with this reading, okay? End up with this reading, trial one, the lower the temperature, the lower the pressure. Let's say we did these measurements up to here, okay? And I stopped doing measurements. I only went down to T equal to 0 degrees Celsius, then I stopped my measurement. Then I'm gonna take another tank of gas, even more dilute, okay? Even more dilute. So this time, I should expect even lower pressure because there is less gas inside, right? So I'm gonna, again, use that to measure the temperature of a substance. And again, the lower the temperature, the lower the pressure. So again, I get a straight line like this. And again, I stop measuring it at T equals 0 degrees Celsius. Now, let's continue this process. Let me use an even more dilute tank of gas and do the same thing, okay? And then I'm gonna get, of course, even lower pressure. And that pressure changes as I change the temperature of the substance being measured, and it goes down to here, okay? Clearly they have different pressure readings for the same temperature because they don't have the same amount of gas inside. The more gas, the more density of the gas, the higher the pressure for the same temperature. However, the beauty of it is that as you extrapolate, okay, not the word extrapolate, as you extrapolate these lines, this line here, for the first extrapolate, you didn't really measure it, okay, but suppose you extend the straight line, it's gonna cross the t-axis at that point. What is the supposed pressure reading at that point? 0, see that, 0. Okay, where does it cross the t-axis? At a very negative temperature. At this temperature, the temperature is so incredibly low, so low that the pressure would read 0. If you believe that the pressure continues to be a linear function of temperature. Okay, at that point, the temperature is so low, the pressure of the gas becomes 0. Wow, can the pressure be negative? Of course not. I mean, the worst you can do for pressure is let it be 0. Now, is that specific to this tank of gas? Well, the answer is no. You can take a different type of gas, look at trial 2, a more dilute tank of gas, and again, you extrapolate that line. Magic. Guess what? It crosses the 0 pressure on the temperature axis at the same exact point. And the same thing can be said for the third tank of gas or any tank of gas. As long as they're dilute, they all agree that when you extrapolate the P versus T curve, they could all cross the t-axis, the temperature axis at that one point, The reading on Celsius scale of that point, negative 273.15 degrees Celsius. There must be something special about this number, okay? This number represents a temperature that's so cold that the pressure of any dilute gas would reduce to 0. Can you get any colder than that? Well, no, because colder would mean that the pressure is even lower than 0, which is negative. That's not possible. Okay, you can similarly design a device based on dilute gas, this time using a constant pressure, but you keep the volume. You change the volume and use that volume change as a measurement of its temperature. And the volume at a given pressure for any dilute gas is also proportional to its temperature. And so this becomes V, okay? This becomes V, not P. P is kept as a constant. And you can do the same experiment, and believe it or not, no matter what kind of dilute gas you use, at that temperature, okay, at that mysterious reading here, the volume of all these gases also shrink to 0. Now, you cannot get a negative volume. It just doesn't make any sense, right? So what that means is that this number here represents what? A temperature that cannot get any lower. Because any lower, you get negative pressure and negative volume, which doesn't make any sense. That is the lowest possible temperature in nature, and it's called absolute 0. Absolute 0, because if I define that point to be 0 of temperature reading, then nothing can be negative on that temperature scale. Everything should be either 0 or positive. That's called absolute 0, and that is the Kelvin scale right here. So the Kelvin scale starts at absolute 0, okay? And on a Celsius scale, that is negative 273.15 Celsius. And on Kelvin scale, no temperature can be possibly negative. Okay, that's something from experiment. And then physicists prefer Kelvin scale because it's guaranteed to be a positive number. And the starting point, the absolute 0, has real physical meanings. It's not just arbitrarily defined. And here I have a chart representing some representative temperatures on the Kelvin scale. Okay, the room temperature, by the way, is typically 20-something, 30-something degrees Celsius, and you add 273 to it, you're getting pretty close to 300. So a typical room temperature is around 300 Kelvin. Keep that in mind. Okay, and you have something really low, lowest temperature achieved by experiment, 10 to the negative 9 Kelvin. Okay, wow, look at this, 10 to the negative 9 Kelvin. Can you get 10 to the negative 10 Kelvin? Yeah, if you have the right technology, you can. Negative 10, negative 11, 10, negative, whatever you want, but you can never get negative number in Kelvin. In fact, you can never get absolute 0 by a finite amount of work. You will learn that later, okay? But let alone a negative value in Kelvin. Now, there is no upper limit in theory. You can get as hot as you want, even though in reality, we're limited by the amount of technology we have. For example, the surface of the sun, the temperature is about 5,700 Kelvin. And interior of the sun can get 10 billion degrees, 10 million Kelvin. And the hydrogen bomb, wow, it's even hotter than that, 10 to the 8 Kelvin. By the way, again, you do not read degrees Kelvin, you just read Kelvin, okay? And so on. It gives you some idea. All right. So these are some typical readings. And so in this first lecture, we talked about what temperature stands for. It's a parameter that determines thermal equilibrium. And we learn how to measure temperature using thermometers, especially ideal gas thermometers with fixed volume. And we learned temperature scales, okay? We still have not touched the actual physical meaning of temperature. What is it that makes two substances stop thermal energy exchange when they reach the same temperature? To understand that, we have to dig deeper into the microscopic nature of temperature, look at the molecular and atomic level. That will not happen until 2 chapters down the line, but at least it gives us some idea macroscopically what temperature stands for. We know from macroscopic point of view, temperature becomes the same if 2 objects are in thermal equilibrium with no energy exchange anymore.